Okay, this is the last example from question 1 in this lecture. Again, we're being asked to draw the products of the following acid-base reaction. We're going to label each compound as an acid-base, acid, conjugate base. And then we're going to determine the direction of the equilibrium. So I'm going to start this out the same way. I'm going to figure out which structure here is going to act as the base. Again, it's pretty obvious in this example. Here's our species with negative charge. That's probably going to be our base here, which means this is going to be the acid. So let's just go ahead and label these things. So base and an acid. And then normally we would evaluate which proton is going to be most acidic on the acid, but there's only one proton on this, so that's the only one that can act as an acid. Hydrocyanic acid has a pK, I don't quite remember, but it's somewhere around 9, so about a pK of 9. It's the only proton that's going to get removed here. So let's remove that. The base is going to grab that proton and leave the 2 electrons between the carbon and the hydrogen on the carbon. So we're going to end up forming this conjugate acid. So this is our conjugate acid. Plus, we're going to form this conjugate base. All right. So now we have everything labeled, and we just want to figure out, which way is this going to go at equilibrium. So again, if we're kind of memorizing pKa's, I'll write this in here again. pK of this is about 9. The pKa of this species is about 24. So remember, the lower the pKa, the more acidic, which means the equilibrium is going to go away from that one. So the equilibrium is going to go away from hydrocyanic acid, the one with a pK of 9. So that lets us know the equilibrium is going to go that way. The other way we can evaluate this if we don't memorize pKa's is we can compare the 2 bases. So we'll compare this species to this species, and we're just going to ask ourselves which one's more stable with the negative charge, because that's the one that's going to dominate here. That's the one that's more stable. It's going to be the one that exists mostly with the negative charge. All right, so comparing the 2 things, we have 1 unit of negative charge on both of these species. That 1 unit of negative charge exists on carbon in both of these. And that 1 unit of negative charge exists on sp hybridized carbons in both of these. So there's not really too much that's different about them, but they clearly have different acidities. And for some reason, this one must be more stable because its acid has a lower pKa, meaning this is more acidic. It's more happy to get removed to form this conjugate base because this conjugate base is more stable. Strength of an acid is directly proportional to the stability of the conjugate base. The more stable the conjugate base, the more acidic the acid was. All right, so for some reason that one on the right side is more stable. Well, let's compare the 2. So here we have negative charge on an sp hybridized carbon. Here we have negative charge on an sp hybridized carbon. The difference here has to do with induction. So we also have an sp hybridized nitrogen. Nitrogen's more electronegative than carbon, especially when it's sp hybridized. Remember, sp atoms are more electronegative than sp2, which are more electronegative than sp3. So here we have an sp hybridized nitrogen. So what that means is it is inductively pulling electron density towards the nitrogen. That's going to help delocalize the negative charge. So that is going to be stabilizing the negative charge. So that's why this conjugate base is more stable. So if we also want to know the direction of equilibrium, we can look at the the bases and compare them. The equilibrium always goes towards the more stable conjugate base.